Joanna Berlińska, and I will be chairing this session on scheduling and load balancing. We will have 4 talks in this session. Each of them will be directly followed by a session of questions and answers. And before we start, let me just remind that questions for the speakers can be asked on our Slack channel, T03 Scheduling. And if you ask the questions already during the talks, then they will be ready as soon as the discussion phase starts, which will make things go smoothly. And now our first presentation is on parallel scheduling of data-intensive tasks. It will be given by Xiao Meng. So please start. And now we will move to the next talk. The next one is entitled Makespan, Lower Bound for the Scheduling of the Tiled Cholesky Factorization based on ALAP scheduling. The presentation was recorded by Olivier Beaumont, but as far as I know, he couldn't be here with us today. So the questions will be answered by one of the remaining authors, Julien Langou. Let's start the presentation.
Okay, good morning, and thank you for attending my talk. So today I will consider the problem of efficiently scheduling Cholesky factorization on homogeneous processors. I am Olivier Beaumont, and this is joint work with my colleagues Julien Langou, Lukasz, and Joanna. So we will consider tiled Cholesky factorization. You have an example of the DAG on the right part of the slide. So this is very typical of many linear algebra applications in the sense that there are plenty of tasks of order n cube, but in fact very different kernels, here depicted by different colors, blue, red, pink, and green, and a very regular but complicated structure. So here you have the DAG for n equal to 5, and then n equal to 8, and n equal to 12 to give you an idea of the shape of the graph when the problem size increases. So our goal in this paper is to find a lower bound on the execution time of Cholesky factorization that would depend only on the execution time of the different kernels on the resource. And we will assume that there is no, that we can fully overlap communications and computations. And we want to obtain a bound which is better than the trivial upper bound that consists on the one hand by the critical path of the graph and on the other hand by the overall work divided by P. So we do this because in order to better understand the dependencies and the parallelism that is induced by the DAG of Cholesky factorization on one hand, and on the other hand, in order to assess the efficiency of the practical implementations that are proposed, for instance, in runtime dynamic schedulers such as WU, DAG, or Quark. So if we look back at the Cholesky graph, we can observe that there are 3 different regimes and 3 different phases. So at the very beginning, there are very few tasks, but this part is very short because after the first POTF, only we have already plenty of tasks. So it's relatively easy to schedule this part because we have plenty of work to do, and keeping the processes busy all the time will be enough. And this is true also for the middle part, and the most difficult part to schedule corresponds in fact at the end when the width of the DAG is smaller than the number of available resources. Then we need to be careful when scheduling this part. So that will be the main idea. So, the first candidate as a scheduler is ASAP as soon as possible, and basically what those one-time dynamic schedulers use is variants of ASAP. So this is a list schedule that keeps the processor busy if there are tasks to do, and so we expect it to be very efficient in the first part of the schedule, but maybe not so efficient at the end. And on the other hand, we have ALAP. So ALAP is as late as possible. So the idea is to perform ASAP schedule on the reverse graph and then to reverse the schedule. So the advantage of ALAP is that we expect it to be efficient for this for scheduling this part of the graph, and we know that when there are no resource limitation, then ALAP provides the optimal running time. So that's the idea on which we will base our approach. So how to obtain a better bound than the trivial bound? So the idea will be to analyze carefully the number of running time, the tasks running simultaneously in the ALAP schedule without resource limitation. So here in orange, that's what is depicted. Here you have the time, and here you have the number of simultaneous running tasks. So if you have more than, for instance, 30 processes in this case, then you have no, in fact, no resource limitation, and you can achieve the optimal time. So you have this for different problem sizes, 10, 20, and 40. And so the idea to analyze the schedule is as follows. You find back the three zones, the beginning where you have very few tasks but which is very short, the middle part which is much longer and where you have plenty of tasks, more than the number of available resources, so you just have to keep the resources busy to obtain a good schedule, and the very end, which might be more complicated to schedule. Okay, and so our idea is to find a close overestimation of this orange plot, and from this overestimation of the orange plot, then we can design a better bound than the trivial bound. So how do we do this? So for instance, imagine that this blue plot is an overestimation of the orange one. So we will first consider the intersection between the green and the blue plots. And we know that for this part of the schedule, then ALAP is optimal. So no schedule can perform more work than ALAP, and so no schedule can leave less work than ALAP to do in this very first part. And so that's the idea of the bound. Here you can find the remaining work in ALAP for the first part, and then this dp corresponds to this to the duration of this. So if we are able to find this blue plot and the intersection between the green and the blue plot, then we can find an efficient lower bound. And then we can slightly improve it by considering what happens at the beginning of the schedule. So that's what we will do in the remaining of the talk. So for each task, the first thing to do is to compute the length of the longest path from this task to the ending task of the graph. So the good news is that if you look at this, then it depends only on one condition, on the relative value of S plus C and G. And what we can observe is that those two cases really correspond to what happens in the CPU and GPU case if you look at the actual running times of the kernels on this. So from this information, we can find for all possible type of tasks the length of the critical path for this specific task. And then the idea is that we know that in a ALAP schedule, the task will run exactly at all the instances that are between M, if M is the Makespan for the ALAP without resource limitation, M minus the critical path, and M minus the critical path plus the length of the task. So you have basically a equation that really defines what the ALAP schedule is. And the idea is now to invert this equation, so given D, to find the set of tasks that are actually running at instant D. Okay, so we will do, and the goal is to do this for all possible types of tasks. So here you have an example of the number of POTRFs, TSMs, CERCs, and GEMs running at different instances. And you can see that it will be easy for POTRF because there is never more than one POTRF running at any instance. But it might be more tricky to find an overestimation of this plot in the case of GEM tasks. Okay, so how do we do this? So for GEM tasks, there is first, so the GEM tasks, there are n-cubed tasks, so they corresponds to 3 different indices that are that must first satisfy this equation, and then there is the other equation. Given D, we know that the task, a given ijk task, will run exactly at this instance. So from this, we can find a unique, in this case, we can find a unique value of k depending on d and I, and then we need to simply count the number of integer points that satisfy this equation. Okay, this set of equations, in fact. And so, in fact, it corresponds to counting the number of integer points in a 2D polynomial. So if you look at the paper, you will see that it's not extremely funny. There are plenty, there are a dozen pages in the research report of such calculations, but it's not very difficult either. And in this case, for instance, you obtain another estimation of the number of gems by a degree 2 polynomial in d square, and the coefficients of the polynomial depends on the running times of the different kernels on the resource. And so does it work? Yes. So that's the result for the gem for the different sizes. Here is the actual number of tasks that run in ALAP schedule without resource limitation. And in blue, you have the number of this other estimation. So yeah, you have it for different problem sizes, and you can do the same for both CPU and GPU cases, and you can do it for all types of tasks, and we obtain this type of plots. Here you have in orange the number of tasks that are running simultaneously, and here in blue the overestimation by our degree 2 polynomial. This is a set of degree 2 polynomial, in fact, depending on the interval. So what is the quality of the bound in practice? So remember the general picture. So we have been able to find an overestimation for all values of D, and then from this we can find a lower bound on the Makespan. So we wanted to prove that ALAP was a good scheduling strategy, and that using ALAP we could find an efficient bound on the number of tasks. So we compared for these different bounds and schedules. So in red and green you have the old bound based on the critical path and the overall work, and in green you have the new bound, and we compared different schedules. In blue ALAP, in yellow ASAP, and then different some other schedules from the literature that are classical for Cholesky. So what we can observe here is that in fact, the green bound and the blue bound are very close here and here. Here you don't have the difference between the yellow and the blue in the GPU case. And so what this proves is that both the bound and the ALAP schedule are very efficient. And the other conclusion is that in the case of GPU, then ASAP schedule is also very efficient. So let's now move to the conclusion. So what we have done is that we have proved a lower bound on the completion time for Cholesky factorization on pure homogeneous processors, which is based on a detailed analysis of ALAP schedule and Cholesky DAG. And it shows that both ALAP is a very good heuristic, that the bound is tight, and ASAP is also a very good heuristic in the GPU case. So this works upon several perspectives. So the first one is to prove an approximation factor for ALAP. So we have seen that ALAP was very efficient, but we have not been able to use this technique to prove this theoretically by proving that ALAP and the bound are extremely close. But we know that ALAP is not always optimal. And the second perspective would be to extend and to automate this technique to other graphs. So at the moment it's much too handmade, too hard, and too long to do it graph by graph. So there should be a way to automate this in order to generalize this approach. And the last perspective is to extend these techniques to heterogeneous techniques. So at the moment we have only the case of p-homogeneous resources. It would be very interesting to extend it to, for instance, k-CPU and k-prime GPU, but it's not obvious to generalize the notion of critical path in this context. So thank you again for attending to my talk, and I will be happy to take your questions.
Okay, thank you for an interesting presentation. We started the discussion and we already have a question from Hatim Multaif on Slack. And the question is, can you please comment on similar bounds for LU or QR factorizations? Julian, are you there?
Yes, can you hear me?
Yes, now I can hear you.
There was a problem, sorry. And hi, hello everybody. And I also want to mention that a co-author of the talk, Alena, is here. So if Alena wants to speak, she's more than welcome to pitch in anything. So I got the question of Hatem Eltaef, and the question is whether we can extend these techniques to QR and LU. The answer is yes, we can. But to go back to the last slide, the goal would really be to try to find a way to do this automatically. So we'd like to, just thank you for doing that. One more, just bullet number, actually, yeah, you're right. Bullet number 2, extend and automate this technique to other graph. Right now, the technique is working, but we have done all the computation by hand, and it has been extremely painful. We hope that, for example, if we use some technique from polyhedric compiler, we can do everything automatically. So that's work in progress. There should be no reason. So basically, those techniques should work very well for Cholesky, but should work very well for any DAG from linear algebra application, which are pretty dense at the top and pretty sparse at the bottom. And the basic idea is to reverse them. That's all.
Okay, thank you. I see someone else is typing, but there is no question yet. So before it appears, I wanted to ask, why did you start with Cholesky factorization? What was the reason to choose it? The structure of the graph? Did you expect that it should be easy to do for this graph? Or
I think it was mostly from, it's a good question. So it was mostly, so the motivation of the authors was mostly, so my co-author was mostly to try to match, Cholesky is a very big test case in numerical linear algebra for scalability of application. So you would see people running Cholesky on, for example, 40 cores and presenting performance graph. And we really were trying to understand what was the limit from a scheduling point of view. So we wanted to do some theoretical work to try to explain the performance results that the community that is doing performance optimization is giving us. So we wanted to find lower bound and try to match. So the next step would be to match those lower bound with real experiments on multi-core platforms, for example. And so that was the motivations. Like people were saying, hey, we got 20%, we can go 20% faster, but we wanted to make sure, and actually I think we proved that actually this 20% from the peak performance can be explained simply because of scheduling reason. It's not possible to expect to have more performance. So that was the motivation.
Okay, thank you. I see an additional comment. It's a comment. Yes, it's a comment from Samuel Thibault saying that they tried some polyhedral analysis with compiler in Lyon over some algorithms, and that people there should be able to do ALAP automatically. So it's a possible collaboration. And I think we have time for one more question. I like this idea of the lower bound and the algorithm validating each other. They are close to each other, so you can see that both are good. Did you do any other research of this type, or maybe you know some other works of this type that where a lower bound is compared with an algorithm and it leads to conclusions about both of them? Or is this more or less unique?
Good question. So I don't really know, actually. I don't know. So it's a good question. Maybe we should have done more bibliography. The truth is that I don't really know similar work. It sounds pretty natural to do that, right? So, but I don't know other works that have done this. So if anybody wants to pitch in some ideas, some reference, they can send me email or they can put them on the chat now. If you look at our bibliography, we don't refer anything. And just to repeat your question, yeah, what we've tried to do is try to find a lower bound on what is the optimal schedule. And we didn't work too much on schedules because whatever well-known schedule we had at hand were actually performing very well and close to the bound. And so that way we can prove some optimality. So if you look at the paper, we can prove that for some pretty small number of cores, like 40, we can prove that between the lower bound, so no schedule can be better than that, and some schedules that are pretty basic, we have a difference about below 3%. And so we think, so another research we'd like to do actually is that when we increase the number of processors, we think that actually we can prove some kind of optimality result asymptotically. And that's something we'd like to look at. Yeah, I don't know of any other work that have looked in that direction, but I would be very happy to know if somebody has some reference for us. That would be great.
Okay, thank you very much. We now have to start the next talk. So thank you, Julian. And now our next presenter will be Alena Shilova, and she will be talking about optimal GPU-CPU offloading strategies for deep neural network training. So let's start.
Hello, everyone. I am Alena Shilova, and today I'm going to present our work called Optimal GPU-CPU Offloading Strategies for Deep Neural Network Training. I would like to start by introducing PlantNet and the examples of the problems that they have encountered. PlantNet is a platform that uses machine learning in order to identify plant species. They train convolutional neural networks that are known to be very efficient for computer vision problems. However, the process of training can be computationally and memory intensive. Memory consumption becomes even more crucial when you train neural networks on the images with high resolution. For example, on the left, you could see the sample of the herbarium dataset. In this task, it is required to detect and count small reproductive structures that could be represented by just a few pixels on the image. Another example is on the right, where the task is to detect and classify weeds, which demands high precision. For this particular task of weed detection, there is an observation that the larger image size, the better quality of the model we can achieve. Thus, there is an interest to use the large image size for the training. However, it can significantly increase the memory needs. Let us find out where the memory problems are coming from. Firstly, let us notice that a neural network can have a very complex structure with a lot of nodes, like you can see on the picture on the slide, where each node could be parameterized. That results in a huge amount of parameters that should be stored. Secondly, the memory issues can arise from the activations or the outputs of the nodes. Neural networks could be viewed in a simplified way as chains. One pass through a neural network from the first layer to the last one is usually called the forward propagation, where the input data is propagated to compute the loss. The other essential part of the training is the backward propagation, the pass from the last layers to the first ones to propagate the error and its sensitivity with respect to the parameters. The sensitivity is measured with the help of gradients. Once all gradients for all weights are computed, they are used to update the weights. However, the gradient computation of backward steps require the activations, the outputs of forward operations. Thus, if we consider forward step F0, here F0 is an execution of the first layer that produces the activation X1, then we should store it somewhere for the later use to perform the backward step B0. The same applies to other activations like X2, X3, etc. Consequently, the memory peak is usually reached when computing loss. At this point, all activation needs to be stored in memory. In order to save memory, different approaches have been developed. For example, mobile nets ShuffleNet, and quantized neural networks are special neural network architectures that minimize the memory used by the parameters. RevNet is a special architecture where there is no need to store activations at all, thanks to reversibility. Memory-efficient batch normalization layers store fewer intermediate values. Used in several machines is an interesting approach that is very popular among data scientists. This includes data parallelism, model parallelism, spatial parallelism, and even their combination. Though it requires to have more than one GPU, and the memory reduction is rather limited, or at the cost of a large communication overhead. In this work, we are interested in how to perform efficient training on one node. There are two popular ways to do it. The first one stores fewer activations but requires to do recomputation of the absent values from the stored ones when needed. The other one suggests offloading activation from the GPU memory to the CPU memory during the forward propagation and then prefetching them during the backward propagation. These two methods, like the previous ones, induce some overhead costs. Nevertheless, they are interesting as they are suitable for training any neural network architecture with limited resources, and even with only one GPU. In our work, we focus on the offloading approach. The idea of offloading was first introduced in VDN and developed by people at NVIDIA. Here they apply a straightforward strategy to decide which activation should be offloaded. They either offload everything or they offload only inputs of convolutional layers. It could potentially impose some unnecessary idle times as the computational operation are synchronized with the communication operation, as it is illustrated on the image on the right. This method was later improved by VDNN Plus of the research group in Bombay. Here the transfers are done asynchronously from computation, which allows to decrease this so-called wasted time. Additionally, they considered memory fragmentation issues and compression to help with the memory reduction. There exist other implementations of offloading techniques such as TFLMS and AutoSwap. TFLMS is a TensorFlow-based module developed by people from IBM Research. In order to perform offloading and prefetching, they use two operations called swap out and swap in. They rewrite the computational graph of a neural network by adding this operation in the proper position. The candidates for offloading are selected based on the distances between nodes. AutoSwap is developed at the University of Singapore. It's implemented in CUDA, and similarly to TFLMS, it uses swap in and swap out operations. To each activation, they assign some priority scores, and they tune these priority scores with the help of Bayesian optimization. And then they offload the activations with higher priority scores. All these approaches were tested experimentally without providing any theoretical analysis to understand in which cases they should work well and in which cases not. Moreover, their choice of candidates is only justified by empirical observations. In our work, we analyze the problem of offloading for the neural network seen as a chain in Figure 3. We describe here the corresponding optimization problem. If we are given an adjoint chain with ALAP operations with non-processing times of forward and backward operation and activation sizes, our objective is to execute this network on the GPU with limited memory size denoted as mGPU, where data can be sent to the CPU at bandwidth beta within the smallest possible time t. Depending on the way we perform communications, we obtain three variants of the problem. What we denote as the main problem is the case when all activations should be offloaded either entirely or not at all, and they can be discarded from the GPU memory only after the transfer is complete. This is the most realistic case. Fractional communication is the relaxation of the memory of the main problem, where the activation should be still offloaded entirely or not at all, but the discards can be performed even during the transfer for no additional overhead. The last case is called the fractional relaxation. Unlike the previous relaxation, it also allows to perform partial offloading, making it possible to keep, for example, one half of an activation on the GPU and one half on the CPU. In this paper, we have considered the complexity of all three problems. We have proved that the main problem is NP-complete in a strong sense. while the fractional communication relaxation is NP complete in the weak sense, and we have designed an optimal dynamic programming algorithm to solve it. We don't provide the description of this dynamic programming, and those who are interested in it could consult our paper for the further details. Finally, the last problem can be solved in polynomial time, and we propose a greedy algorithm that produces the optimal solution for this problem. Let me briefly explain the idea of our greedy algorithm. The picture on the slide shows an example of how the memory profile evolves within the one iteration depending on the operation in process. The memory peak is reached somewhere during the backward propagation. In order to cross this peak, while we only have limited memory available, which is mGPU, we need to offload at least mpeak minus mGPU data to the memory of the CPU. Intuitively, in order to avoid a large overhead due to a communication, it is required to communicate as early as possible. We actually prove in our paper that the fractional relaxation, the optimal schedule is no wait, eager, ordered, and sends an amount of data exactly equal to mpeak minus mGPU. Here, no wait means
so in the second volume of Harry Potter, correct me if I have any of these details wrong. Remember, there's that snake,
first activations,
the basilisk.
and ordered that we,
so this is magic cat.
of the indices. Activations are performed as soon as possible, eager that we offload only the first activations, and ordered that they are offloaded in the increasing order of the indices. Let us notice that in fractional communication relaxation, there exist cases where the optimal schedule is not eager, which makes the solution of the problem more complicated. However, the optimal is still no wait and ordered, and we use this property to build the dynamic programming. To compare different methods, we have run the simulation for the different types of convolutional neural networks. The solution of the greedy and dynamic programming algorithms for the corresponding relaxations are adjusted to get the solution of the main problem by computing the no-wait and ordered schedule which offloads the same set of activations. Here on the figure you can see how the relative Makespan changes with the mGPU. The relative Makespan is obtained by taking the ratio of the measured Makespan to the lower bound defined below. This lower bound is equal to either the total computational time of both forward propagation and backward propagation, or the computational cost to offload and prefetch the data that doesn't fit. TFLMS is represented only by one dot because it crashes for the lower memory cases. The plots clearly demonstrate the advantages of our suggested methods over the previously known state-of-the-art. The dynamic programming approach shows the best performance as it is based on the relaxation, which is the closest to the main problem. Furthermore, we compared offloading as a technique in general with the normalization. The plots show throughput with respect to mGPU and its evolution depending on the values of the bandwidth. From this figure, we can conclude that normalization is more efficient than offloading for small values of the bandwidth and no memories. Yet, with the larger bandwidth values, offloading brings better performance than rematerialization, making it more promising. That brings us to the end of my presentation. To sum up, we showed that it is important to reduce memory consumption when training neural networks. Furthermore, storing activations could be even more expensive than storing weights. This makes offloading a promising approach, as it is allowed to store fewer activations at the cost of the overhead imposed by communications. In our work, we have established the NP completeness in the strong sense of the main problem, and NP completeness in the weak sense of the fractional communication case. We found a dynamic programming algorithm to solve fractional communication relaxation and the polynomial greedy algorithm to solve the fractional relaxation. Finally, we have shown by simulating a large variety of cases that we outperformed the previous state-of-the-art techniques. In our future work, we would like to validate the obtained results throughout real experiments. And also, we would like to combine offloading with robotization and consider offloading on the nodes with multiple GPUs. Thank you for your attention.
Thank you, Elena. We are now waiting for some questions from the audience on Slack. I see someone is typing. But before the question arrives, I wanted to ask some theoretical questions. So you proved weak NP hardness for one variant of the problem, strong NP hardness for the main problem. And I wanted to ask if you had to do something untypical, or could you just use some standard problems for the reductions?
Hello, Joanna.
Hi.
Thank you for your question. We indeed use just classical examples. For example, to prove NP completeness in the strong sense, we used three partition. Mm-hmm. So we transformed our initial problem to the case of the three partition problem. And for NP completeness in the weak sense, it was two partition problem.
Okay, thank you. And I was also wondering what the actual complexity of your dynamic programming is. It's pseudo polynomial, but I wondered how bad or how good is it? Is it possible to use it in practice for smaller instances, or is it something really bad?
Usually it's possible to use it for all our instances that we proposed in the experiments, even for the lone chains. And I think it depends very on the discretization scheme, because we use some continuous variables to define our dynamic programming. And so in order to discretize these values, we used, I think, 500 points for each continuous variable, mm-hmm. Which gives around 20 seconds to find the solutions for each problem.
Okay. And I have one question coming actually from the reviewers. So how difficult would it be to integrate your algorithms in some real frameworks like PyTorch or TensorFlow?
That's a very interesting question. So as far as we understand, in PyTorch, it probably would be more difficult, because all the binaries, all the communication between the GPU and CPU, they are hidden inside the language. So it requires probably the direct communication with the developers of PyTorch. And we also considered a bit TensorFlow. For example, we could do something similar to the same way as they did with TFLMS. They do the swap in and swap out operations, but it requires the rewriting the graph. And also the problem that we discovered with TensorFlow is that we don't know how to schedule precisely the operations at which particular moment. So which probably makes it a little bit complicated to integrate, but that's would be interesting future work.
Okay, thank you. I saw someone was typing on Slack, but the question is still not there. Oh, okay, it's now. So the question is coming from Paul Kelly. Have you considered compressing the activations?
We haven't considered that, but I think it's a valid approach, because I think in one of the related work, when we did related work, we noticed that some researchers, they proposed the combination of VDNN with compression, but in our work we decided to concentrate on the theoretical analysis of the obtained problem.
Okay, thank you. And we still have time for one more question. So the title of your talk is Optimal Offloading Strategies, and you have the exact algorithms for these two relaxed versions of the problem. Have you tried checking what is the theoretic performance of these strategies you designed for the general problem, or do you just have the computational experiments, simulations, and this is just how you validate it? this, or could you get some theoretical results for your strategies too?
We didn't consider that, but so we just provide the simulations.
Okay, and do you plan to run now some real-world experiments too? You said that adding the algorithms to TensorFlow would be complicated, but not that bad using PyTorch. So do you plan to do that, or just go further with simulations?
One of the possible way to do it, we considered, for example, NVIDIA, they don't provide the integration to TensorFlow or to PyTorch. They just code it themselves, the offloading techniques. And so one of the ways to, for example, to do the same way with our technique, but that demands more time. And so that's, but as I mentioned in the last slide, it's one of our future work.
Okay, thank you. And to finish the discussion on this paper, I will also read a remark from Paul Kelly, who just wrote that this topic is somewhat related to the best paper, Maximizing I/O Bandwidth for Reverse Time Migration on Heterogeneous Large-Scale Systems, which will be presented tomorrow. So it may be something interesting to listen to. So thank you very much, Elena.
Thank you.
And now we are moving to our last talk in this session. The last presentation was prepared by Xiangjiang Gu, and the title is Improving Mapping for Sparse Direct Solvers, a trade-off between data locality and load balancing. Please start.
Hi, welcome to my channel. My name is Xiangjiang. I'm going to introduce a work about improving mapping for sparse direct solvers, a trade-off between data locality and load balance. Sparse matrix solvers are going to solve the linear system AX equals to B, in which A is very large and sparse, lots of zeros included. Generally speaking, there are direct methods and iterative methods. In PaStiX, a direct matrix solver considered in this work, the solving is composed of a sequential analyze step and a parallel factorization and solve step. We focus on the scheduling and mapping phase in this work. At a cross-grain level, the computation is represented as a tree of supernodes, where nodes represent computational tasks and edges represent data dependencies. If we room the supernodes, we can find that the supernodes are composed of many small tasks, which themselves form a small, direct acyclic graph. At the scheduling and mapping phase, we map processors to tasks. The first step is to map a subset of processors to supernodes. Then a processor in the set will be selected for each task of a supernode at the second step. In this way, we can exhibit tree level and load level parallelism and reduce the scheduling complexity. Let's see the first step. Proportional mapping is a widely used classical approach to solve this resource allocation problem. Follow a top-down way, it assigns processors to a branch of nodes according to their relative weight. Let's see an example. On the left-hand side, we have a tree of supernodes. The weight of the whole tree is 100. At the beginning, all processors from P0 to P8 are assigned to their root node. Then half processors are assigned to the left branch, because its weight is exactly the half of the whole tree. The same goes for the right branch. This process continues recursively until reach the leaves of a processor, or a processor is assigned to a whole branch. Proportional mapping is good at perceiving data locality. A processor may be assigned to a node and its ancestor, so we do not need to move the output files. But it's bad at node balance. Processors can be used only for the branch they are assigned to. Different branches have different parallelism capability, even if they have the same weight. Some branches are hence idle, some processors are hence idle, while other branches cannot benefit from these processors. Let's say an example. So we have 10 processors at the big. We have 10 processors. We assign all them onto the root. According to each branch's relative weight, proportional mapping maps 4 processors to the left branch and 6 processors to the right branch. The right branch only has 5 tasks, so processor P9 is idle. However, the left branch has 5 tasks. One of them can be assigned onto processor P9. An intuitive solution is to assign all processors to all tasks. We call it auto heuristic. It solves this node imbalance problem, but it's complex and incurs lots of data movements. This work is going to answer the question, how can we improve the node balance while keep good data locality? We can solve it in the second step. Let's say the second step. The aim of the second step is to decide the precise mapping for each task. In PaStiX, this is done by simulating the actual factorization based on the prediction of both the running times of tasks and of the time needed for data transfers. After the first step, as you can see now, a set of processors has been mapped onto each task. Each processor is equipped with 2 priority queues, ready queue and waiting queue. Ready queue stores tasks that have received all input files. Waiting queue stores tasks that have received part input files. Tasks inside will be sorted by an increasing ready time. Since leaves don't have any dependencies, they are in the ready queue at the beginning. Each processor has a ready time. It represents when this processor finishes the current job and can start another job. Each task also has a ready time. It is calculated as the time it receives all input files from its successors. At each step, the scheduler compares the first task of all ready queues and selects the one who can start earliest. Then it updates ready time of processors and queues. So right now, we can select task M, task I, task H, task J. We randomly select one because they all can start at the same time. We select task G and we run it on processor P0. Then we update the ready time of processor P0 as the finish time of task G. And then task C will be inserted into waiting queue of processor P1 and P0 as they receive part input files. Then we select the task who can start earliest, task H. We schedule it on processor P1. Then we select task I. We update ready time of processor P2 and the waiting queue of processor P2. We continue this process. At each step, we select the tasks who can start earliest, and then we update the ready time of the processor and the queues. So right now you can see that the ready queue of processor P0 and P1 are empty. Continue this process. We schedule task A, and finally we schedule task R. So then the whole mapping is finished. You can find the idle states of processors very easily. We can find that processor P0, P1, and P2, they have some idle times, idle slots. So if we can reduce these idle slots, then we can make sure that each processor has as many work as possible. Let's roll back to where the idle comes from. At this step, ready queue of P0 and P1 are empty, so no task will be mapped onto them. If we can steal some tasks from other processors, processor P0 and P1 may have something to do. Let's take processor P0 for example. Next task will be mapped onto processor P0 is task A. The idle slot can be calculated as the ready time of task minus the ready time of the processor. To reduce this slot, the task we steal should start earlier than task A. But task B can start earlier, hence we schedule task B onto processor P0. The idle slot is then reduced. The same analysis goes for processor P1. And finally, the task A can start earlier. Let's summarize the steal technique. At the moment, if the ready queue of processor P is empty and the ready time of the first task in waiting queue is strictly larger than the ready time of processor P, we predict that there will be an idle slot. To reduce this idle slot, we copy tasks from labor processor's ready queue. In order to reduce the movement in a distributed environment, we steal tasks that are on the same cluster. For testing our heuristics, we conducted the experiment on 34 large sparse metrics from various fields. The scheduling strategies considered include all-to-all as a reference, and the proportional mapping, the classical scheduling algorithm, the one we proposed, steal, and a variant that prefers stealing tasks on the same MPI node, steal local. Let's check the results. Those two figures show the data movements between different MPI nodes. The left figure is the number of communication. The right one is about the volume. X-axis shows the different MPI settings given. For example, 2M12 represents 2 MPI nodes and 12 threads. The number and volume of communication of steal is the same as proportional mapping and far lower than the reference algorithm all-to-all. And those two figures show the performance on the data movements inside an MPI node. Steal and steal local have more data movements than proportional mapping, but less than reference heuristic all-to-all, especially the number of data movement. Those two figures show the simulation cost. You can see that all-to-all is far costly than others. Steal and steal local have almost the same cost as proportional mapping. Steal and steal local are slightly faster than proportional mapping according to the estimated factorization time. Finally, let's check the real factorization time in a shared memory environment. As you can see that steal has the same performance as all-to-all and is slightly better than proportional mapping. In conclusion, the algorithm we proposed reduced the communication frequency and volume and slightly reduced the final factorization time. In this work, we revisit the classical mapping strategy, proportional mapping. To solve the load imbalance of proportional mapping, we proposed the steal technique-based dynamic scheduling algorithm. Extensive experiments on real software PaStiX shows that our method achieves a good trade-off between data locality and the load balance. For the future work, we expected a better performance of our algorithm in a distributed environment. As the communication is more expensive, so we will perform further experiments on distributed platforms. We also plan to propose some novel strategies to further improve performance. Thanks for your attention.
Thank you very much for an interesting presentation.
Hi.
Hello, nice to hear you in person now. We are now waiting for some questions from the audience. And I wanted to start by asking what exactly is the difference between your steal and steal local algorithms. I think you said that steal local prefers using stealing from the same MPI. But does it prefer only? So is it possible to also steal work from somewhere else, or is it just local stealing or nothing? Because I am not sure.
Hi, Joanna. So I'm Changjia. Thanks for your attention and introducing. The answer is for steal local, it only steals processors who shares the same memory. Could you hear me?
Yes, I can hear you. Thank you. And do we have questions? No, we don't have questions on Slack yet. So another thing that I am not sure about, and the slide where you presented schedules with pink pictures, trees, I noticed that I think a bit later, because we are moving, oh yes, somewhere here. Is this here? Yes, these slides a bit later when we already have a part of the schedule. I can see that some parent nodes can be started before their children finish. So is this because they are super nodes and they don't need the whole output, or what happens here?
So
for example, C can start before G finishes. So is this because they are super nodes and not all data are necessary?
Yeah, it's because they are super nodes. So as I introduced before, the super nodes are composed of some small tasks. So only part of, so after part of the small task finish, it receives all the input files, so it can start its work.
Okay, I see. So actually, in this picture, we don't see this information about how big a part we need. But okay, I get it. So you don't need the whole output to start this parent supernode. Okay, thank you. This clarifies a lot. Okay, one more question. You said that in your stealing procedure, you only steal from 1 or 2 neighbors. I guess this is done to keep the locality not that bad, but have you tried some other numbers like why 2? Maybe just 1, maybe 3 neighbors. Did you just pick it, or did you try other variants too? Of the number of neighbors from which the number of nodes from which you can steal some jobs.
Yes, I understood the question. Why I didn't try any other options. So first of all, the stealing technique is after the proportional mapping. So the scheduling are already good enough, and if this processor doesn't have any other work, probably the neighborhood, if their 2 neighborhood processors do not have any other work, probably 3 or 4 or 5, we also do not have any other works to do.
Okay, thank you. And one last question, I think. The experimental results, are they all for shared memory, or are some of them for distributed memory too?
Okay, this is a very good question. The results are composed of 2 parts. The all results of 4 results before they are from the analyze step, so they include the shared memory environment, and the final result, the final factorization time, it is on shared memory. So we will do that experiment on for the distributed memory soon.
Okay, thank you. Let me check. I see no further questions. So I guess this will be the end of our discussion. Thank you very much. I would also like to thank all the presenters for preparing the videos. This must have taken a lot of time, so thank you very much. Thank you for answering the questions. And I would also like to thank the audience for participation and for asking questions. And now we will have a short break. And the keynote by Eva Dielman starts at 5:30, so I hope to see you there. Thank you. Bye.